Before I begin with today's class, let us revise what are the topics that I have covered in the last class. The first thing I spoke about was the physical properties of amines, under which I spoke about the physical state, solubility and boiling temperature. Then we have the chemical properties. The amines are said to be reactive in nature because of two reasons. The first reason is the presence of a lone pair of electrons, and the second one is the large difference in electronegativity between nitrogen and the hydrogen atom. Then we discuss about the first chemical property, that is the basic character of amines. Amines are said to be basic in nature because it has a lone pair of electrons for donating. And this basic character is measured in the form of Kp and pKb value. If a compound has low pKb value and high Kp value, it is said to have high basic strength. So Kp and pKb are inversely proportional to one another. Then we discuss about the comparison of basicity between alkane amines, aryl amines and ammonia, out of which alkane amine has the highest basicity because of presence of alkyl groups, which is an electron donating group. In the case of aryl amines, there's a presence of electron withdrawing group, due to which the basicity decreases. And then we compare the basicity between different groups of alkane amine compounds. In that case, you have primary amine, secondary amine and tertiary amine. Now, for that you need to consider the phase in which it is present. If it is present in the gaseous state, tertiary will have the highest basicity, followed by secondary and then primary. Whereas in the case of liquid state, you need to consider three factors. The first one is plus I effect, the second one is the solvation factor, and the third one is the steric hindrance. So considering all these three, the sequence of basicity will vary. Therefore, when an experiment was conducted, it was seen that the amine containing methyl group, in that case secondary will have the highest basicity, followed by the primary amines and finally the tertiary amines. Whereas in the case of ethyl amines, the secondary will have the highest basicity, followed by the tertiary and then the primary amines. These two are in the case of liquid state. So that is about the basicity of amines. And then we discuss the second chemical property, that is acylation, with the help of acyl chloride, with the help of an ester, and with the help of acetic anhydride. So these three we have done. Then we did the alkylation reaction, where addition of alkyl group takes place and the primary amine gets converted to secondary and secondary gets converted to tertiary amine. So that's all about the last class. Now in today's class, I am going to discuss about the fourth chemical property, that is the carbylamine test or carbylamine reaction. And it is called as test because it is used to identify whether your compound is primary amine or not. So only the primary aliphatic and primary aromatic will give this reaction, whereas secondary and tertiary amines will not show this reaction, and tertiary will not show this reaction. So in this case, what happens is, when you take a primary amine, RNH2, and react it with a chloroform, CHCl3, plus in the presence of ethanolic KOH, and when you heat it, it forms RNC plus ACl plus H2O. So when you balance this equation, you have got 3 chlorine atom on the left hand side, whereas in the case of right hand side there is only 1 chlorine atom. So you have to multiply this with 3 and 3 potassium over here, and number of hydrogen atom is 4, 5, 6. So multiply this with 3. So in this case, you can see that there's a formation of RNC compound, which is called as isocyanide compound. Now this has a foul smell. Therefore, from the smell of the product formed, it indicates that the given compound in the reactant state is a primary amine. because of the formation of isocyanide, this is also called as isocyanide test. And it is shown only by primary aliphatic and primary aromatic amines. So therefore, if you are given a two compounds, one is primary amine, one is secondary amine, now you will have to write a test for that. So for the primary amine, you can give this test, that is carbylamine test. So this is about the carbylamine, the fourth chemical property. Okay, then the next chemical property is reaction with nitrous acid. In this case, primary, secondary and tertiary amines reacts differently with nitrous acid. With nitrous acid, HONO. Now let me take a primary amine. Primary amine, let's say I have an aliphatic primary amine, RNH2. When it reacts with HONO, which is produced when sodium nitrite reacts with HCl. So this reagent is prepared very freshly. It is prepared by treating sodium nitrite with HCl. Now what happens is when primary aliphatic amine is treated with nitrous acid, a diazonium salt is formed, that is RN2 plus Cl minus. Now the aliphatic diazonium salt, here aliphatic diazonium salt is formed. Salt is formed, which is very unstable. So this on hydrolysis, it produces alcohol, ROH plus hydrogen gas is evolved and plus HCl. Water consists of OH minus and H plus. OH minus will react with this R and form ROH, that is an alcohol, and this H plus will react with the Cl minus and it produces HCl, and this N2 is evolved in the form of gas. So this is in the case of primary aliphatic amine. Now if I take a primary aromatic amine, let's say I have benzene diazonium chloride, NH2. Now this is aromatic, whereas this one is aliphatic. So when I take a primary aromatic amine with nitrous acid, sodium nitrite with HCl, this produces HONO, which reacts with this and converts this primary aromatic amine to a diazonium salt, in this case benzene diazonium salt. So this is benzene diazonium salt plus, and the byproduct form will be NaCl plus H2O. So this is quite stable compared to the aliphatic diazonium salt. Now this reaction takes place at a low temperature, that is 273 to 278 Kelvin. So this is about a reaction of nitrous acid with primary amine. The first one is with an aliphatic primary amine, which gives an unstable aliphatic diazonium salt, and on hydrolysis it produces alcohol, nitrogen gas is evolved and HCl is produced. Whereas in the case of primary aromatic amine, it reacts with nitrous acid to produce aromatic diazonium salt, in this case benzene diazonium salt plus NaCl and H2O. So this is about reaction of primary amine with nitrous acid. Okay, now let me take secondary amine. In the case of secondary amine, let's say I have R2NH. Now this will react with nitrous acid, HONO, which is again produced by reacting sodium nitrite with HCl. This will form nitrosoamine, R2N, N double bond O. This is called as nitrosoamine. In the secondary, in the case with reaction of secondary amine with nitrous acid, it forms nitrozoamine. Whereas in the case of tertiary amine, it forms plus HONO, nitrous acid. It will form a nitrite salt, that is, this N will pick up hydrogen from here, R3NH plus NO2 minus. A nitrite salt is formed in the case of tertiary amine. So you can see that in the case of primary amine, you get a diazonium salt, whereas in the case of secondary amine, a nitrozoamine is being formed, and in the case of tertiary amine, a nitrite salt is formed. So this is how you can use this reaction to distinguish between primary amine, secondary amine, and tertiary amine. Okay, then the next chemical property is reaction with aryl sulfonyl chloride, and this reagent is also called as Hinsberg reagent. Now in this case, only primary and secondary amines will show this reaction, whereas tertiary amines will not show this reaction. So this can also be used to distinguish between primary, secondary, and tertiary amines. So let me take a primary amine first. You have your reagent, that is aryl sulfonyl chloride. Now when this reacts with a primary amine, I am taking an ethyl group instead of R, H and H. Now this sulfur will connect with this nitrogen atom. For that, this pi electrons will shift onto the oxygen atom. O will have a negative charge and this S will have a positive charge. Now on this positive charge sulfur atom, nitrogen with a lone pair of electron will come and attack, and you will get SO with a negative charge, and this chlorine atom, double bond O, this nitrogen atom, H, and C2H5. Since nitrogen is losing its lone pair of electrons in forming bonds with this sulfur atom and will have a positive charge. Now in order to stabilize the positive charge on the nitrogen atom, this hydrogen will leave in the form of H+, and this bonded electrons will sit back in the form of lone pair of electrons. And this negative charge will come and form a bond over here, and this chlorine will leave in the form of Cl-. And the product formed will be S double bond O, and N, H, lone pair of electron is back, and then your ethyl group C2H5, and this two will react with one another and it forms HCl. Now in this case, you have a sulfonamide which contains a hydrogen atom on the nitrogen, and this hydrogen is said to be acidic in nature because it is located next to an electron withdrawing group which pulls the electrons from the nitrogen atom, which in turn try to pull the electron from this group, because of which the bond between nitrogen and the hydrogen becomes polar and it is easier to donate the hydrogen atom. So due to which it is said that it makes the entire group soluble in alkali solution. So because of the presence of H+, it is soluble in an alkali solution. Whereas in the case of secondary amine, you don't have hydrogen atom over here. Instead, you will have a C2H5, and because of the absence of hydrogen atom in the case of secondary amine, this product will be insoluble in the alkali solution. So that makes all the difference. So if you name this compound, this will be N-ethyl benzene sulfonamide. It is N-ethyl benzene sulfonamide. That's about reaction of primary amine with aryl sulfonyl chloride. Now let's take a secondary amine where you have a C2H5 instead of one hydrogen atom. The reaction mechanism is same. Okay, I'm taking a secondary amine now. S double bond O Cl. When you react this with a secondary amine C2H5 and C2H5H and the lone pair of electrons. Now again, this will shift. O will have a negative charge, S will have a positive charge. Now this nitrogen with a lone pair of electrons will come and attack this sulfur, and you will get SO with a negative charge and the chlorine atom. Sorry, it's only one bond. Chlorine atom, then you have a double bond O, and this nitrogen will connect with this sulfur. So N, one hydrogen atom. I'll write it on the top, and then you have C2H5. Now nitrogen will get a positive charge because it is using its lone pair of electrons, so N will have a positive charge. Now in order to stabilize the positive charge on the nitrogen atom, this H will leave, and again this bonded electrons will sit in the form of lone pair, and this Cl will leave in the form of Cl minus because back bonding takes place. And the product form will be S double bond O, and lone pair of electron is back, C2H5. Now here there is absence of acidic hydrogen, absence of H plus, due to which it is insoluble in alkali solution. And if you name this compound, it is NN-diethyl benzene sulfonamide. Since you have two ethyl group as a substituent, so this will be NN-diethyl benzene sulfonamide. So you can see that in the case of primary amine, the product formed was soluble in alkali solution, whereas in the case of secondary amine, the product formed will be insoluble in alkali solution. That's why you can distinguish between primary and secondary amine using this test. Okay. So that's all about reaction of amines with aryl sulfonyl chloride. Is a primary ingachina kerana product valdo di khariolana alkali base solution. Also the alkali the base ni kimana kebar khariolana alkali ladi sambala base which is dissolved in water. In the solution chicken could dissolve is primary ingachina because of the presence of hydrogen atom. This is secondary ingachina and the hydrogen needed sambala ko khariolana insoluble areas. Primary the secondary ever chidan and tertiary amines ingachina and the reagent the foreign angle reagent chi this. Okay, then the next chemical property is the seventh one, that is electrophilic substitution reaction. Aniline undergoes electrophilic substitution reaction. The reason for this is aniline acts as an electron-rich compound. So, in this case, if you draw the resonating structure for aniline, this lone pair of electrons will come and form a double bond over here. Since you cannot have double bonds together, this will shift and sits in the form of negative charge on this carbon atom. So you will get double bond NH2. This will sit in the form of negative charge. Now what happens is, again, this will form a double bond over here, and this sits in the form of negative charge, and you will get double bond NH2, double bond over here, and this will sit in the form of negative charge over here, and this same thing. Now what happens is, again, this will come and form a bond over here. Since you cannot have two double bonds together, this will shift and sits in the form of negative charge over here. Double bond NH2, double bond here. Now double bond comes over here, double bond, and then you have a negative charge over here. Again, now this forms a double bond over here. Since you cannot have two double bonds together, this will go back and sits in the form of lone pair. Okay. And lone pair NH2. So if you number this is the first resonating structure, second resonating structure, third resonating structure, fourth, and then the fifth one. Okay, now what happens is, in this case, you can see that the negative charges are delocalized on the first carbon, second carbon atom. This is your second carbon, and then it is on the fourth carbon atom, and here it is on again 1, 2, second carbon atom. So all the ortho position, ortho refers to second carbon, para refers to fourth carbon atom. So you can see that the second carbon atom, the fourth carbon atom, again the second carbon atom, all of this have negative charge. So whenever electrophile comes, it always comes and attack this carbon atom, second, fourth, and second. Ortho and the para positions are attacked by the electrophile, due to which NH2 is also called as activating group, or it is also called as ortho-para directing group. Because NH2 directs the incoming electrophile either at the second carbon atom or at the fourth carbon atom. The aniline ki number ba NH2 igyo jwa ko khari la or na chidane namgyu ngazo sik di pijuchi activating group ta ortho-para directing group la di pijuchi khari chinna nitrogen kana electron ni igyo di benzene kana teche ko resonance jwa ki liba de. Those should sambala lone pair ki tambonya na quality lana dela ni double bond form jai. That double bond di dela chana dela double bond tamboni dwa. Double bond ni nyam to le middle sambala di dele dela negative form di. That the negative the answer le di kora can draw di ba. Delocalization of electron takes place here. The daily to sambala dela double bond chai. Double bond ni nyam to le middle sambala di dele ni dela negative chai. Dus chine kora ganya negative daily to sambala kuni number de middle sambala di ya do. Dus chine tama dela kera thambo di kanti yo di ro structure di ba. Ta dus tadi sambala ngani nga number la negative charge di ko kwale chana na carbon thambo carbon niwa kana le ro. Dus tadi carbon thambo niwa suma shiva kana chike do. Ani dene ya niwa kana na chale do thambo niwa chine. Kaji carbon thaga chi di sambala and you do carbon dene because this is the principal functional group. The those change and carbon niva gama negatively re carbon shiva gama negatively re and carbon niva gama negatively re samala. That chilon electrophile jile orwa electrophile and electron yung tagyoji electron ma isala attack chigali ba. The attack chigali re samala call attack chigala nga yue dina carbon 2 yorwa 2 chazana 2 mare. Rosa di carbon niva che, carbon shiva che, carbon niva. Kari chinna na khonso kana kari yorana negative charge di delocalized cha di samala and electrophile chilo nelego di kadu na yama ortho product form chere yama para product form chere. This okay. Now I'm going to explain some of the electrophilic substitutions shown by this compound. The first one is bromination, where bromine acts as an electrophile. The first type of electrophilic substitution, that is bromination. Then there is nitration, where NO2 acts as an electrophile. And then there is sulfonation, where the sulfonyl group acts as an electrophile. So I'm going to first explain bromination, then I'll go to nitration and sulfonation. So in the case of bromination, okay, now in this case, you are going to treat aniline NH2 with bromine water Now what happens is here Br plus acts as electrophile. Now this Br can attack either the fourth carbon atom or the second carbon atom or the fourth carbon atom, but when you treat it with bromine water, the ring is activated in such a way that bromine will come and attack all the second and the fourth position. So you will get a compound where bromine occupies both the ortho position and the para position. So this compound is named as, this is suppose is your first carbon atom, second, third, fourth, fifth and sixth. So you have second, fourth and sixth. 2, 4, 6 tribromoaniline. So you have got a tri-substituted compound where the hydrogen atom on 3 of the carbon atom has been replaced by the bromine atom. But you don't want that to happen. So you want only mono-substituted compound where you want only one bromine atom to come and attack one carbon atom. So for that you have to control the activating power of the NH2. So for that you are going to treat NH2 with acetic anhydride. We have done that in acylation reaction. So when you treat this with acyl group, double bond O, OC double bond OCH3 in the presence of urethane, what happens is again, this double bond will shift. O will have a negative charge and this carbon will have a positive charge. Now on that, this nitrogen with a lone pair of electron will come and attack and you will get N is using its lone pair of electrons in forming bonds with this carbon atom. So N is going to have a positive charge and then this carbon O with a negative charge and this CH3 group, and you have your O, C double bond O, CH3. Okay, now in order to stabilize the positive charge on the nitrogen atom, this H will leave in the form of H plus and N will get back its lone pair of electrons. And again, this back bonding takes place and this entire group will leave, which will combine with the H atom and form ethanoic acid. Now in this case, I'm going to get a product where you have NH, I write it over here, NH, one pair of electrons, C double bond O, CH3. Okay, now in this case you can see that N has got a acyl group attached to it. Now because of presence of this acyl group, now N has got an option to undergo resonance with this compound as well. So because of presence of acyl group, this lone pair of electron gets engaged in forming resonating structure with this compound. So therefore, the activating power of nitrogen on this aniline group is reduced. So when you treat this compound with bromine water, what happens is mono-substitution takes place. So in this case, you will get a compound in which bromine will attack only the fourth carbon atom, that is para product will be formed. So you are going to get a mono-substituted compound, NH, and then you have your C double bond O, CH3, and a bromine on the fourth carbon atom, that is the para carbon atom. Now the question is, why para compound instead of the ortho compound? The reason for this is this entire group acts as a steric hindrance, which causes the difficulty for the bromine atom to come and attack this carbon atom because of its large size. So it causes a steric hindrance for the incoming electrophile. Whereas in the case of para-carbon atom, there is no such bulky groups present around this fourth carbon atom. That's why it can easily come and attack the fourth carbon atom, because of which you are going to get a para product instead of both ortho and para. So now you want to have your product that is without this group. So for that you are going to treat it with a base or H plus, and you will get your NH2 with a lone pair of electron and then your bromine atom. So you have got a para-bromo aniline as the main product. Para-bromo aniline. Para because first, second, third and fourth carbon atom. Fourth carbon carries the electrophile, which is your bromine. So para indicates the fourth position. On the fourth position, bromine is present. Therefore, para-bromo, and this compound is aniline. So para-bromo aniline. That's how you are controlling the activating power of NH2 by treating it with an acyl group. So when an acyl group is present, this lone pair engages in undergoing resonance with this group, because of which it has less activating power on this ring. So because of which the ring is less activated, therefore only mono substitution will take place. Whereas in the absence of this acyl group, this lone pair is completely engaged in forming resonating structures with this compound, because of which all the ortho and the para position gets activated and you get tri-substituted compound. So that's how protection of aniline is done. This is called as protection of aniline. Protection of aniline group is done to control its activating power on the benzene ring. Okay, that's about the bromination. Now moving to nitration again. The same thing happens. Again, you have to control the activating power of NH2, and then you are going to treat it with the nitrating agent, which is concentrated H2SO4 plus concentrated HNO3. Now next one is nitration. Again, the first step you need to do is to control the activating power of NH2 so that you will get a mono substituted compound. Now for that you have to treat this compound with acetic anhydride, C double bond O CH3 in the presence of pyridine. Now again, this pi electrons will shift. O will have a negative charge, this carbon will have a positive charge. Nitrogen with a lone pair of electrons will come and attack this carbon atom, and you will get NHH. Now N will get a positive charge, and on this, connect this with this carbon C, O with a negative charge, bring the CH3 at the bottom, CH3, and then you have O, C double bond O, CH3. Now, in order to stabilize the positive charge on the nitrogen atom, this H will leave in the form of H plus. Now this negative will come and form double bond over here, and this entire group will leave, and which will react with hydrogen atom, and it forms ethanoic acid. Now you will get a compound where you have NH, and lone pair of electrons is back, and then you have your C double bond O CH3. Now this is protected aniline compound, where again the lone pair of electrons on the nitrogen engages in undergoing resonance with this group, because of which its activating power on the benzene ring is controlled. So since you have controlled the activating power, now you can treat this with your nitrating agent, that is concentrated HNO3, concentrated nitric acid, plus concentrated sulfuric acid, H2SO4. This will generate an electrophile which is NO2+. That's why it is called as nitrating agent, which provides NO2+. Now this NO2+ will again come and attack the carbon which is on the fourth position. Because of the steric hindrance, it cannot attack the second carbon atom. So the product formed will be a para substituted NH, C, double bond O, CH3, and NO2 on the fourth position. Now in order to remove this group, you are going to hydrolyze this and you will get NH2 and NO2 on the fourth carbon atom. Now if you name this compound, first carbon, second, third and the fourth carbon atom. So this will be para nitro aniline. Para nitro aniline. This entire group is aniline. So that's how you have nitrated aniline by protecting the aniline group. Okay, now the question is, what if you don't protect the NH2 group on the benzene ring and carry out nitration? So in that case, you will get a mixture of compounds, concentrated HNO3 plus concentrated H2SO4. You are going to get a mixture of para product, which is in 57%, and then you are also going to get meta product, that is NO2 group on the third carbon atom. Meta means third carbon atom, NH2. This is 47%, and you are going to get an ortho product in which you have NO2 on the second carbon atom. Now this product is 2%. So the question is, NH2 acts as an activating group, and we just learned that activating group will always direct the product at the ortho or the para position. But in this case, there is the formation of meta product being formed. So sometimes you will be asked why there is a formation of meta product taking place when you treat concentrated HNO3 and concentrated H2SO4 with aniline. So for that, the reason is, when aniline is treated with this reagent, what happens is there is a formation of aniline taking place. The nitrogen on the lone pair of electrons will pick up H plus from this, and it forms anilinium ion, and nitrogen will get a positive charge. This is called as anilinium ion. Now this anilinium ion acts as a deactivating group because of NH3. It acts as a deactivating group, and deactivating groups are always meta-directing. Meta-directing, that's why it directs the NO2 at the third carbon atom, that is first, second and the third carbon atom. That's how you are getting a mixture of ortho product, para product and meta product when you carry out nitration without protecting the NH2 group over here. So that's all about nitration. And after nitration, it is sulfonation under electrophilic substitution reaction. Now in this case, you are going to treat aniline with the sulfonating reagent, which is concentrated sulfuric acid, H2SO4. Now what happens is, this gets converted to anilinium hydrogen sulfate, NH3 plus HSO4 minus. This is called as anilinium hydrogen sulfate. H2SO4 consists of H plus, HSO4 minus, and with a lone pair of electrons will form bonds with this hydrogen atom. That's how it gets converted to aniline hydrogen sulfate. Now, this on heating, a molecule of water gets removed. Now, from this one hydrogen atom and from this one OH combines together to form a water molecule, and it leads to the formation of NH2 SO3H. Now this is called as para-amino benzene sulfonic acid. Okay, how does this happen is when the aniline is treated with concentrated H2SO4, it leads to the formation of aniline hydrogen sulfate. After removal of the water molecule from this, it undergoes rearrangement. So rearrangement takes place in such a way that SO3H group will come and sits at the fourth carbon atom and leads to the formation of para-amino benzene sulfonic acid or para-amino benzene sulfonic acid. And then this can also exist in the form of zwitterion. Zwitterions are the compounds in which you have both positive ion and a negative ion. So in this case, I have NH2, which picks up hydrogen from this, and it leads to the formation of NH3 plus and your SO3 minus. So you can see that this molecule consists of both positive ion and a negative ion. So in this case, this is called a zwitterion. This can also revert back to this state, or this can also exist in the form of zwitterion. So that's about sulfonation, where you're adding a sulfonyl group by using concentrated H2SO4. Now with this, we are done with the chemical properties of amines. Now moving to the final topic of this chapter, that is diazonium salts. Di stands for 2, azo stands for nitrogen atom. A salt containing 2 nitrogen atoms, diazonium. So in this case again, we are going to study the preparation of diazonium salt. How are you going to prepare diazonium salt from amines? Preparation of diazonium salt preparation, then you will have the chemical reactions shown by diazonium salt, or the chemical properties. Okay, now in this case, let's start with the preparation. Under preparation, you have to treat amines with the diazotization reagent, that is sodium nitrite with HCl. Now let's take, I have RNH2, a primary amine. When you react this with HONO, and you get this when you treat sodium nitrite, NaNO2 plus HCl. When this two reacts, it leads to the formation of nitrous acid, which will react with your amine, and it forms RN2 plus Cl. This is the diazonium salt, a salt containing 2 nitrogen atoms. Now let's take a aromatic amine. Let's say I have aniline. When you treat aniline with sodium nitrite, NaNO2 plus HCl, now these are added freshly during the reaction. Now this leads to the formation of HONO, which is your nitrous acid. And when this reacts with nitrous acid, it forms benzene diazonium chloride, N2Cl. Benzene diazonium chloride. Okay. That's how you are converting amines to a diazonium salt, by treating with NaNO2 plus HCl, because of which this is called as diazotization reagent. NaNO2, sodium nitrite plus HCl acts as a diazotization reagent which converts amine into diazonium salt. If you are taking an aromatic compound, you will get an aromatic diazonium salt. If you are taking a aliphatic amine, you will get an aliphatic diazonium salt. So the diazonium salt is always named in this way. You will first take the name of the hydrocarbon followed by the word diazonium, and finally the suffix will be the anion. So in this case, benzene is the hydrocarbon part, benzene, diazonium, and the name of the anion, benzene diazonium chloride. Let's say I have C2H5, N2 plus Cl minus. Now the name of this salt will be, hydrocarbon part is ethane, so ethane diazonium followed by the name of the anion, that is chloride. So ethane diazonium chloride, in this case benzene diazonium chloride. First name of the hydrocarbon followed by the word diazonium, and then finally followed by the word of the anion. Benzene diazonium chloride when you have a benzene, N2NCl minus. Ethane diazonium chloride when you have a ethane, N2NCl. So that's about the naming of the diazonium and the preparation of the diazonium salts.